Welcome everybody to our next video. Today we're going to be talking about the fundamental counting principle, and probably the best way to start that off, to give you an idea of how that works, is to give you an example of where it might be used. And so let's suppose that we've got a committee that consists of 5 people. So we've got Alice, Dave, Bob, Eugene, and Carol. And from this group of people, here's the problem, from this group of people, in how many ways can we select a president and a secretary? Now, kind of one way to do that is to take all of the people in our committee, Alice, Bob, Carol, Dave, and Eugene, and to be systematic and just write out all of those possibilities. And so kind of going through each one, well, if we pick Alice as being president, then we could have Bob as a secretary, Alice and Carol as a secretary, Alice as president, Dave as secretary, Alice as president, and Eugene as secretary. Or if we select Bob as president, then we can have Alice as secretary, Carol, Dave, or Eugene as secretary. If we pick Carol as secretary, and so on and so on and so on. And so if we are systematic and write out all of those possibilities, when we count them all up, we see that we do have a total of 20 possibilities. Now, actually writing out all of the possibilities is always an option, but the numbers could be so big that actually writing out all of the possibilities may be really hard to do. It may take too long to actually do it. And so in that case, it would be better if we had kind of a shortcut way of actually doing this, and that's where this fundamental counting principle is coming into play. So what the fundamental counting principle says is that there are n possible ways of performing one experiment A, and there are m possible ways for performing experiment B. Then if we do those experiments together, first we do A, then we do B, then the total number of ways for the new experiment is going to be the product of the number of ways for each individual experiment. And so let's see how that applies to the situation we just encountered. So what we have 2 positions. We have a position as president, and we have a position as secretary. If we look at our total number of choices for choosing president, well, we've got 5 people in our group, so we've got 5 choices for that one. Now, when we then turn to the secretary and we look at how many choices that we have 4 choices because we've already chosen the president. So the president's gone. We made that choice out of 5 people, so we've got 4 people left for the choice of secretary. And so the fundamental counting principle says that we've got a total of 5 times 4, or 20 possible choices. And that's exactly what we found whenever we were systematic and wrote each one of them out individually. Another case where we would use the fundamental counting principle is writing out words or letter sequences. So another question might be, how many 3-letter sequences are possible using the letters A, B, C, D, and E if you are not allowed to repeat any letters? So the setup is pretty much the same. We have 3 different choices. We have the first letter, we have the second letter, and we have the third letter. If we look at our number of choices for each one, well, we had the letters A, B, C, D, and E, so we could have any of those as our first letter. So we have 5 possible choices for the first letter. Now, we're not allowed to repeat any letters, and so for the second letter, we've already chosen one for the first letter, so that letter is gone, so we only have 4 possibilities for the second letter. We get to the third letter, again, 2 letters are already gone, so we only have 3 possibilities for that letter. And so the fundamental counting principle then says that how many total options, how many total choices do we have? Well, 5 times 4 times 3. Well, 5 times 4 is 20, times 3 gives us a total of 60 different words, 3 letters long, with the letters A, B, C, D, and E. And now we kind of begin to see that it really doesn't take very long for the number of possibilities to get pretty large. And what we're seeing here is kind of a systematic listing of all of 60 of those possibilities. Now, we can go a little bit further, and if suppose we didn't want just 3-letter sequences, we wanted 4-letter sequences. Well, now we're adding on another case, and so our numbers keep getting bigger and bigger and bigger. Or if we were asked, if we were allowed to use any of the 26 letters to make our words, then again, our number of possibilities is going to be so large that just writing each one of them down is just going to take too long and just not even possible to do it. So we need a way to be systematic and a way to calculate that without having to write out every single one. So kind of a third case of where we would use the fundamental counting principle is imagine that we are rolling 2 fair 6-sided dice. So for the first die, we see that we've got 6 possibilities. For the second die, we also have 6 possibilities. So the fundamental counting principle says we multiply those together. So 6 times 6, we have a total of 36 possible outcomes. Now, when we represent all of those, kind of, in this case, I show it represented as ordered pairs. So the first entry in the ordered pair is going to be the value that you get on the first die. The second entry in the ordered pair is going to be the value that you get from the second die. Kind of looks like those ordered pairs that we would remind us of when we were graphing lines and talking about slope and those kind of things. But if we are systematic again and write out all of our possibilities, we see that sure enough, yes, we do end up with a total of 36 possibilities. Now, kind of a question that could come from that then is how many ways are there to roll either a sum of 2, 3, 4, 5, all the way up to 12? Well, we've written out all of our possible outcomes. So here again, we see the table. We've got all of our possible outcomes written. Then if we just add up all of those possibilities, or take the sum of each of those numbers in the ordered pair, and that tells us what our sum would be on our roll. So if we look at kind of this diagonal, a 3 and a 1, a 2 and a 2, a 1 and a 3, that's, all of those are going to give us a possibility of rolling a 4. A 6 and a 1, a 5 and a 2, 4, 3, 3, 4, 2, 5, 1, 6 gives us the possibility of rolling a 7. And so just like the 6 and the 5 and the 6 are the only ways that we can roll an 11. So that if we would do this, if we kind of put all of that information in the table, we write out our sum, our number of ways, and our probability. So again, just to remind you a little bit of what our probability is, it's going to be the number of ways that the event can happen divided by the total number of things in your sample space. Well, we've got 36 possible outcomes from our experiment, so we know that our denominator is always going to be 36. So how many ways can we roll a 2? Well, there's only one way. You can roll a 1 and a 1. How many are to roll a 3? 2 ways. To roll a 4, 3. To roll a 5, there are 4 ways. To roll a 6, there are 5. To roll a 7, there are 6 ways. To roll an 8, 5, 9, there are 4. 10, there are 3 ways. 2 ways to get an 11, and only 1 way to get a 12. And so if we then look at the probabilities for those, what is the probability of rolling a 2? Well, it's 1 divided by 36, so kind of approximating the decimal there, 0.02778. Probability of rolling a 3, 2 out of 36, 0.05556, and so on and so on. And so we can kind of see that the most likely roll, the one with the biggest probability, 6 over 36, is just going to be 0.16667. So how would these kind of start showing up then if we went and rolled a lot of dice? So what we do then is to roll a pair of dice, and we're going to roll it 1,000 times. So that's exactly what we did. And so looking at those results, how many times did we get a 2? How many times did we get a 3? We can see that we had a 2 28 times, a 3 55 times, 4 we had 91 times, 116 5s, 136s, 162 7s, 157 8s, 111 9s, 76 10s, 54 11s, and only 20 12s. So if we look at our empirical probabilities, so our probabilities from actually performing the experiment, so that's going to be the number of times that we got a particular outcome divided by the number of times that we actually performed the experiment. So our empirical probability of getting a 2 would be 28 divided by 1,000, or 0.028. Now, if you remember, the theoretical probability of getting that 2 was going to be 0.02778. So it's pretty close, actually, to our theoretical probability. For the number of 3s, the theoretical probability was 0.05556. What did we get? 0.055. Again, really close. For number of 4s, 91 over 1,000. That theoretical probability was going to be 0.08333, and we got 0.091. Pretty close, again, to our answer. Number of 5s, and if we kind of go back, you might want to go back and write down all of those probabilities that we had previously and kind of really do the comparison there. But in rolling that dice, rolling those pair of dice 1,000 times, we get empirical probabilities that are pretty close to our actual theoretical probabilities. And so our counting scheme for actually doing it and developing this mathematical model with 36 possible outcomes really does give us, really does reflect what we find when we actually perform the experiment. And so kind of a last place or a last example that we'll do where we can use the fundamental counting principle is talking about license plates. So suppose that we know that a license plate has a particular pattern to it. It's got a pattern of one letter followed by 2 numbers, followed by 2 letters, followed by a number. And so the question is, how many license plates are actually possible? So for the solution to this, well, we first say how many letters are we allowed to have? Well, A, B, C, D, all the way up to Z, we're allowed to have 26 possible letters. For the numbers, we can have any digit 0 to 9, and so that gives us 10 possibilities for our numbers. And so by the fundamental counting principle, we have letter, number, number, letter, letter, number. So we have 26 times 10 times 10 times 26 times 26 times 10, which actually gives us a grand total of 17,576,000 possible license plates. And so for that configuration, so this is really truly an example of we would not want to have to exhaustively write out each one of those to see how many we were actually going to have. Being able to compute it with some kind of counting principle gives us a real shortcut, because we couldn't write that number. We couldn't write out all of those possibilities. It would take us forever. We would never get finished. And so this is where counting comes in to make our lives much easier. So hopefully this has been a little bit of an introduction to the fundamental accounting principle and give you some examples of where we might use it. See you all next time.